All right. Second half of the review. So we finished up the other half with reactions. So here is moles. So this is calculate the molar mass. Remember, the molar mass is the mass of one mole. So basically, we have one Fe here and three Cl's. So the mass of one mole of this is going to be equal to the sum of that molar mass on the periodic table. So one Fe is 55.85. 3 Cl's, each Cl is 35.45. So we're going to multiply that by 3 and add it to 55.85. 55.85 plus 3 times 35.45.
That would be 162.2.
So we get 162.20 grams equals 1 mole. So for this, if we have parentheses, that means there's 2 of these PO4s. So there's 2 P's and 8 oxygens and 3 calciums. So 3 times 40.08 plus 2 times 30.97 plus 8 times 16.
That would be 310.18.
So this is 310.18. Here we have 5 carbons and 12 hydrogens. 12 times 1.01 plus 5 times 12.01.
It's 72.17.
Oh, 17. There we go. So here we just have 8 sulfurs. So we're going to look on the periodic table. Find sulfur, 32.06. Multiply that by 8. 32.06 times 8.
It's 256.48.
Here we have 1 strontium, 2 nitrogens, and 6 oxygens. 6 times 16 plus 2 times 14.01 plus 87.62.
The answer is 211.64.
All of these are in grams. It's the mass of 1 mole. Here we have 2 ammoniums. So that's 2 nitrogens, 8 hydrogens, 1 carbon, and 3 oxygens. 3 times 16 plus 12.01 plus 2 times 4 times 1.01.
It's 68.
I'm going to go ahead and redo that one. 2 times 14.01 plus 8 times 1.01 plus 12.01 plus 3 times 16.
It's 96.11.
There we go. Cool. Now it says to calculate the percent by mass. Well, any percent is a part divided by the whole. So to calculate the percent by mass of each element in strontium nitrate, we need the whole. Well, we have the whole right here, 211.64. We're going to divide that by 1 strontium, 87.62. 87.62 divided by 211.64 times 100.
It's about 41.4004.
Remember, we times that by 100 to make that a percent. Now we're going to do the nitrogen. So that's 2 times 14.01, which is 28.02. And we're going to divide that by the whole as well. And times it by 100. 28.02 times 28.02 times jeez, did it again. 28.02 divided by 211.64 times 100.
The answer is about 13.2394.
So 13.24. And then we got to do the oxygen. 2 times 3 is 6 times 16. 6 times 16?
That would be 96.
So 96 divided by 211.64 times 100. 96 divided by 211.64 times 100.
It's about 45.36.
45.36 plus 13.24 plus 41.40.
The answer is 100.
So that all adds up to 100%. Therefore, we're probably correct on that. Next question says determine the mass percent of oxygen in this. So again, we need to add all those up. We did it up here. 96.11 grams. we're going to take the amount of oxygen. 3 times 16.
It's 48.
So it's 48. 48 divided by 96.11 times 100.
The answer is about 49.9427.
So it's 49.94% on that. Down here we have empirical formulas and molecular formulas. So this is circle all of the molecular formulas that could have the empirical formula NO2. So basically NO2 is everything reduced. So 2 and 4 are both divisible by 2, and that would become, if we did that, N2O4 would become NO2 if we divided both of those. 2 and 5 do not have a least common multiple that's a whole number. 3 and 5 are the same way. 3 and 6, the least common multiple is, the greatest common factor is 3. So that, again, would give us 1 and 2 if we divided both of these by 3. What is the empirical formula of a compound that contains 86.4% carbon and 14.4% hydrogen? Well, first thing we do is we change that to grams. And then we need to change the grams to moles, and basically we're going to make a mole ratio. We're going to divide by the smallest number of moles. Excuse me. So this is carbon. This is hydrogen. 12.01 grams is 1 mole of carbon. 1.01 grams is 1 mole of hydrogen. 86.4 divided by 12.01.
It's about 7.194.
14.0. 14.4 divided by 1.01.
That would be about 14.2574.
Excuse me. So if we take a look, we want to divide both of these by the smallest one, which would be 7.194. I'm going to pause this for a second. All right, let's try again. So 14.26 divided by 7.194. 14.26 divided by 7.194.
The answer is about 1.9822.
Still not over it. So that is a 1 to 2 ratio. The 1.9 will round up to 2. And then we will get CH2. That is the empirical formula of that. The next one says it has percents. It wants us to do the same thing, basically. So we'll change that to grams. And then we'll change the grams to moles. So every 39.10 grams of potassium is 1 mole of potassium. Every 12.01 grams of carbon is 1 mole of carbon. Every 16 grams of oxygen is 1 mole of oxygen. 56.6 divided by 39.10.
It's about 1.4475.
8.7 divided by 12.01.
The answer is about 0.7243.
34.7 divided by 16.
The answer is about 2.1687.
So we look at these, we find the smallest one, and we divide them all by that. So in this case, it's 0.724. And basically, this makes a ratio 1 to something. This is our 1 to something to something. 1.45 divided by 0.724.
It's about 2.0027.
2.17 divided by 0.724.
It's about 2.9972.
So there we have 2 to 1 to 3. So it's 2 potassium to 1 carbon to 3 oxygen. All right, next we have conversions of moles to mass and stoichiometry. So how many atoms are in 1 mole of any element? Well, the number of particles in 1 mole is 6.02 times 10 to the 23rd atoms, or particles if you're talking about molecules. So how many silver atoms are in 1.2 grams of silver? So we have 1.2 grams of silver. And the thing is, to find the number of atoms, we've got to first get grams of silver to moles of silver. So 1 mole of silver is the atomic mass of silver. So we find silver here, 107.87 grams equals 1 mole. And then if we take a look, every 1 mole of silver then is 6.02 times 10 to the 23rd atoms of silver. Can't do that in the old calculator watch, so we got to pull out the calculator, and this will be a good example of how to type that in. So 1.2 divided by 107.87 times, since it's on top, we times it by 6.02 times 10 to the 23rd. That comes up to 6.70 because it rounds up. Only 2 significant digits, so 6.7 times 10 to the 21st atoms. How many moles are in 15 grams of barium acetate? So we're going to have to add all that up unless we have it over here. We don't have it over there. I wish we did, but we don't. So there's so many grams in 1 mole of barium acetate. And that's what we need to find out. So we have to add them all up on the calculator. So barium is right here. 137.33 plus 4 times 12.01 plus 6 times 1.01 plus 4 times 16.
It's 255.43.
15.80 divided by 255.43.
The answer is about 0.06185.
So there we have it. That's how many moles are in 15.80 grams of barium acetate. What is the meaning of 3H2 plus 1N2 yields 2NH3? That's saying that 3 particles of H2, 1 particle of N2 will make 2 particles of NH3. But we could say 3 dozen particles of H2 plus 1 dozen particles of N2 yields 2 dozen particles of NH3. Or we could say 3 moles of H2 reacts with 1 mole of N2. For the following reaction, how many moles of SO3 could be produced from 1.90 moles of O2? So we start with what we're given every time, 1.90 moles of O2. We look every 3 moles of O2 makes 2 moles of SO3. 1.90 times 2 divided by 3.
The answer is about 1.2666.
1.27 moles of SO3. This next one has, instead of starting with moles and ending with moles, it starts with grams and ends with grams. So we need to go from grams of aluminum to moles of aluminum. And then every 2 moles of aluminum, we make 3 moles of hydrogen. And every 1 mole of hydrogen weighs 2.02 grams from the periodic table. And every 1 mole of aluminum weighs 26.98 grams from the periodic table. 12 divided by 26.98 times 3 divided by 2 times 2.02.
It's about 1.3476.
2 significant digits, so 1.4 grams of hydrogen. Consider the following. If we use 3 grams, how many moles will we produce? Well, again, we are doing the same idea, the same concept. This time we're starting with grams of sodium bicarbonate. And we're going to moles of CO2. Every 1 mole of sodium bicarbonate, 3 times 16 plus 12.01 plus 1.01 plus 22.99.
The answer is 84.01.
Weighs 84.01 per mole. Every 1 mole is 1 mole. That's kind of boring. We're done. 3.0 divided by 84.01.
It's about 0.03571.
Again, 2 significant digits, so 0.036. What is the percent yield of a product in reaction where the theoretical yield is this? So we have 36.25 grams. That's what we should have. That goes on bottom. And the 32.65 grams is what we actually got. That goes on top. So it's actual over theoretical times 100. Basically, this is like what you got on a test versus how many points it's worth. 32.65 divided by 36.25 times 100.
The answer is about 90.0689.
So our theoretical yield is 90.07%. Not bad. The limiting reagent is the product that runs out. Nope. It's not the product that runs out, it's the reactant that runs out. So it's the reactant that runs out, and it's the reactant that determines how much you can form. It's the limiting reagent. Reagent is another word for reactant. So obviously these product ones would not be something you would be looking at. Thermochemistry. So if we take a look here, you need to know that mass times specific heat capacity, or MS delta T, is equal to Q, or the amount of heat. If heat is absorbed, it's endothermic and delta H is positive. If heat is released, it's exothermic and delta H is negative. So this is how much heat must be added to 75 grams, which is our mass, to increase the temperature from 25 to 1535. 1535 minus 25?
It's 1,510.
So there is our delta T. And here is our heat capacity, our S. So this is iron, so iron specific heat capacity is 0.451. We're solving for Q. Q equals 75.0 grams times, I'll do the specific heat capacity first, 0.451 joules per grams degrees Celsius times 1510 degrees Celsius. 1510 times 0.451 times 75.
The answer is 51,075.75.
51,000, looks like we have 3 significant digits, so it'd be 51,100 joules. Everything up here cancels out except for joules, giving us our unit. Is this endothermic or exothermic? Well, what's happening to the temperature? The iron block is increasing in heat, so this is absorbing energy, so that is endothermic. Down here we have our heat curve. I'm going to go ahead and make that line the 0 degrees Celsius. I think that just the printout looks a little bit weird. But the gas phase, the gas is going to be the highest energy phase, so that's where the gas is. The liquid phase is going to be the middle. Remember, you can only change temperature when you're in one state of matter. These flat lines refer to changing of a state of matter. So this would be the liquid. It's the middle stage. And the coolest stage will be the solid. This is where melting and freezing happen. That means that both solid and liquid exist here along that line. Notice there's no temperature change while that's occurring. Vaporization and condensation occur on B. What is the melting point? Well, we look for the smallest, the flat line at the bottom. So the melting point is 0 degrees Celsius. If I move that change up, what is the boiling point? We look for the flat line between liquid and gas. So that is 100 degrees Celsius. During the process of change phase, what happens to temperature? Temperature stays constant. It does not change. The temperature stays constant. Now keep in mind, going from solid, that's the lowest amount of energy. Let's do this. So going from solid to liquid is called melting. Going from liquid to solid is called freezing. Going from liquid to gas.
Mr. Jackson, about the thermal lab.
So liquid to gas is called vaporization. And gas to liquid is called condensation. Now there is another crazy one where solid goes directly to gas. That's called sublimation. Or when gas goes directly to solid, that's called deposition. It's made after the word deposit. So like if you deposit something, you kind of put it there. Deposit, deposition. And basically it's just depositing that solid along the wherever it's collecting at. So that is the second half of the final exam review pack. Good luck on finals. Have a great day. Bye.